can't I do this? Please. I can only draw circles on whiteboards. Okay. That's good to know. All right. Put a little point there. I'll make a little chunk. I see someone's in, but I'm waiting a little bit longer to really start talking. I guess I'll get some definitions down. You guys are going to see my handwriting progress while I work on this. My handwriting on this tablet is awful. Okay. Radius is something we'll need. What else? What else are we going to need? Radius. We're going to go arc. Arc measure. Arc length. We'll do that for now. Alright, what time is it? Okay. Wait another minute or so for at least one more person to join, if there's going to be someone. How do I select things? Can I do that? Undo that. What does this do? Nope. Okay. So this review today should only be about an hour. It shouldn't be any longer than that. We are going to be going over some basics of only specific aspects of circles. If you're joining now, I haven't started yet. Welcome. I'm going over some circle information and geometry. I am teaching directly towards a specific test, so I'm not going to hit everything. I'm only going to hit the things that are necessary for that test. Before we get into what we're getting into today, I have some definitions here. Radius. The radius of a circle. So let me go ahead and attempt. I'll try that again. Attempt. Close enough. Here's a circle, and here's a point in the center. A radius is the distance from the center of the circle to the edge. So any line that goes from the center to the edge of the circle is a radius. Distance from the center of a circle to the edge. And since the point in the center should be the same distance from all sides, my drawing is not accurate, but if it was a perfectly drawn circle, the distance from the center to the edge would be the same on no matter what radius I drew. So all radii is the plural, so I'll put that here. Radii equals 2 or more radius. So if I have more than one radii, these technically should be the same length. My drawing is just bad, so it will not look as accurate as this what should be. So when you have two radii connected to a center, you get this little pie, this little pizza slice. Right here, this distance, or this little part of the circle, the edge here, I'm going to highlight it actually. This edge here, that's not highlighted. There we go. This little chunk, this edge here, is called an arc. So I will go ahead and say the part of a circle that connects the endpoints of at least 2 radii. And that's kind of what we're going to focus on today, is how arcs work. There are 2 aspects to arcs that we're going to focus on: arc measure and arc length. I am actually going to rewrite these in different colors so we can differentiate them easier when we're doing the math. So arc length we'll do in red. Or sorry, arc measure. arc measure. Arc measure is the degree measurement of this arc, and it's denoted by the letter N. I couldn't tell you why. That's a little degree symbol. I couldn't tell you why it's the letter N. That's just what we use. Arc measure is the degree measure of an arc. So what does that mean? So usually when we look at degrees, we're either talking about temperature, which we're not, or angles. And right here at the center of the circle, we have an angle that's created by the two radii. That is called, I'll put a little arrow going towards it, that is called the central angle. And what's nice about the arc measure and the central angle is that these will always equal each other. The central angle is the same measurement as the arc. What's a nice way of thinking about it is like pretend you're standing at the center of a circle, like in a circular room, and you're pointing to a spot on the wall where someone else is standing. And that person walks from one point to another, and they stop. The entire time you're pointing at them. You're pointing, your arm is pointing, and it's pointing, and you stop. That angle measurement that your arm moved is the central angle and also the arc measure. So it's also the angle measurement of that arc. The actual distance, please select it, thank you. The actual distance that was walked, so from point A to point B, that distance that was walked along the side is called the arc length. Distance of the arc. So again, measure is if you're pointing at someone in a circular room and they move from one point to the other. The measure is the angle measurement that your arm essentially pointed at and moved. The arc length is the actual feet that person walked from point A to point B. It's how many steps they took. So arc measure is denoted by, like I said, the letter N. I'll put a little degree so you know. And arc length, for reasons unknown, to me at least, is denoted by the letter S. I don't like that it's denoted by the letter S because it looks like a 5, especially with my handwriting. But it is, and I couldn't tell you why. And honestly, it's not that big a deal as to know why. When it comes to arc measure, there's no, equation. It is just they are related to the central angle. It is a degree measurement. You just need to understand that the arc measure is used in other equations. And an equation that it is used in is the arc length equation, which I will write here. Hopefully it looks good. So I am going to go crazy with this tool that I'm not used to yet. Okay. Arc length, again, denoted by S, is equal to the arc measure, denoted by N, divided by 360 times 2 pi r, or r is your radius. I should put that up here. Radius is denoted by r. So what this is saying is you have two pieces of this equation. You have this fraction where you have your arc measure divided by 360, and you have this little chunk of things being multiplied. 2 times pi times r. Now, 2 pi r on its own is its own equation, the circumference. The circumference is the distance around a circle. Essentially, if I was to give you, or you were to look at, I don't know, the stupid giant sphere in Vegas, and you got the distance around it and how long it took you to walk around it, however many feet that distance is the circumference. So that's what this piece here is, the circumference. This piece here is the arc measure divided by 360. So if you don't know, all angle measurements in a circle add up to 360. 360 degrees. The reason for that is because when geometry was kind of made, it was, I believe, Egypt, and Egypt used base 60. Not necessary for you to know, but what you need to know is 360 is the amount of degrees if you walked all the way around. So if you're standing at the center and you point at someone and they walked around the entire circle, the degree measurement would be 360. Now, that being said, right here we're dividing our arc measure by 360. Well, why? Well, our arc measure is only a small chunk of the circle. It's only, I'll just draw it here. Whoa. Oh my God. Nope, I got this. Oh, nope. Okay, last one. Whatever we get, we're using. Okay, fine. Okay, I'll draw another arc here. Those are connected. I will highlight the arc. I should put it on a different spot where they're connected. You understand. Okay. The arc here is a small section of our circle. It's only a small little chunk. It's a percentage of the circle. This kind of looks like it's a quarter of the circle. It's a little less than that. But essentially what this fraction is the ratio of how much this part of your circle is compared to the whole thing. So how much degree measurement is part of the whole thing is this chunk. So what you're doing is multiplying the circumference, the entire distance around, times whatever percentage of the distance is, or whatever percentage of the circle is here, the degrees. I know that's kind of weird to understand. It might be a little hard to grasp what I'm trying to say, but we'll do an example. So let's go ahead and assume some numbers. I will say that the radius here, so the distance from the center to the edge, is 10. We'll use an easy number, 10. And we'll say that this central angle is 45 degrees. We'll use another easy number. 45 degrees. If the central angle is 45 degrees, so the arc measure must also be. Arc measure is equal to the central angle. So we're given the central angle is 45, so the arc measure is also 45. The radius, the distance from the center to the edge, is 10. All we need to do is plug that into this function. So let's go and do that. We're looking for arc length. We know that our arc measure, our n, is 45 degrees, so that goes on top. Times 2. And when you see things touching each other like this and there's nothing in between, that just means they're multiplying, so I'll write that here, times pi times r. R is our radius, so let's look. Look at that. We have our radius, 10. So we have 2 times pi times 10, and also times this fraction. Well, I chose 45. I know I said it's an easy number. It's easy because it goes into 360 very simply. Let's see. 90 times 2 is 180. 90 times 3 times 4 is 360. So this reduces actually to 1/8. 45 goes into 360 8 times. So if I divide both of these numbers, 45 divided by 45, any number divided by itself is 1. 360 divided by 45 is 8. These are the same exact fraction, just one is with simpler numbers. When it comes to multiplication, you can multiply things in any direction you want. So 2 times pi times 10 can be done as 10 times 2 times pi. I like to combine my numbers and leave pi as is. 2 times 10 is 20, and we got pi. Even easier, we can just put this all into one fraction. 20 pi over 8. That's a pi. It's going to bug me. 20 pi over 8. This can also be reduced if you'd like. You have even numbers here. They are both divisible by 4. So what we could do is 20 divided by 4 is 5. And 8 divided by 4 is 2. So honestly, all of this, you can plug this into a calculator if you'd like. This part right here is already ready to be calculated into a calculator. The only reason why I would do a calculator for this is because of pi. Pi is an infinitely long decimal point. Normally, I would say just don't do calculator stuff, but we have pi, so we have to. You can plug this in here. It can be difficult to plug in stuff into a calculator if you don't know where your parentheses are going or what don't call me hashtag pi guy. That's the worst. Oh my God. You lost my train of thought. That stun locked me. Anyway, this can be plugged in. It can be difficult too. I like to reduce things as far as I can. This is the most reduced it can be. So at this point, I am going to open up my calculator, and it's 5 pi over 2. And you can literally type it in that exact way. I'm going to make sure 5 pi is in parentheses. 5 pi divided by 2. 7.85. 7.85. I'll reduce it to that. So my arc length here, the distance that I would walk from this point to this point, is 7.85. Give me 1 second. That is essentially the basic arc length. It's where you just plug in your two values where they need to go. There's going to be a couple more problems that we do where we're going to solve for missing things. Where did I get the 5? That's an 8. Sorry. Where did I get the 5 pi over 2 if I just had 20 pi over 8? I reduced the fraction. So let me do it over here. So I had 20 pi over 8. It's a bad writing 8. So both 20 and 8 are even numbers. So I know it can be reduced by 2. Or I can divide both of them by 2. But if I divide them by 2, I get 10 pi over 4. Those are also even numbers. I can divide them by 2 again. 5 pi over 2. It was just reducing the fraction. This is just a bad 8, so it might have looked like a 9. So that's my bad. 8. That's even worse. Oh my god. There it is. All right. Other question. What if I have no angle? I'm so glad you asked that because we're going to do an example with no angle. So this is how you do it, where if you have an angle and you have a radius. But if you don't have an angle, we can use this equation to solve for it. But you need at least 2 pieces of information. So if we don't have an angle, we need the arc length and the radius. I am going to move forward and attempt another circle. Fine. Okay. This time we're going to... Oh, God. Drawing tablets are very difficult. All right. There's a horrible... I'll just make the dot bigger so it looks fine. There is a little arc there. I got asked just now, what happens if you don't have an angle? So let's do that. Let's say we have the radius of, I don't know, 5. And our arc length, so the distance. Let's say our arc length is, I'm just going to make something up, 13.4. And we don't know the measurement. The arc measure, the central angle, we don't know what that is. We can still use the arc length equation to do this. The only difference is we're not going to plug in the arc measure and the radius. We're going to plug in the arc length and the radius. Arc length this time is given to us as 13.4. We don't know n, so we leave it up top. You don't need to put the degree next to n. I'm just doing it there so you understand that it's an angle. Times 2 times pi times our radius, 5. Great. If you didn't know, when you have a fraction multiplying to stuff like this, essentially all of this is being divided by 1. And so you have 2 fractions that are being multiplied. When you multiply fractions, the tops and bottoms multiply together. So I'm going to rewrite it. 13.4 equals n times 2 pi 5. N times 2 times pi times 5 over 360 times 1 is 360. I like putting it all into one fraction because it lets me know immediately that I can cancel out the denominator. Canceling out can be a weird concept to understand. I'll do a quick example over here in a different color. Canceling out example. Let's say I have 100 is equal to x over 5. So some number divided by 5 is 100. I know a lot of you will look at that and be like, well, 500, get it. Fine. Yeah, you're right. But the math that you actually did in your head and what you need to show is actually called canceling out. When you have x over 5, this is a fraction, and all fractions are division. X is a number you don't know. 5 is the number you're dividing it by. If you're dividing something by something, if you want to get rid of the thing you're dividing by, you do the opposite. You multiply by that number. Now, I'm putting over 1 here just to let you know what's happening. I'm going to show every single step that happens here. Usually when you multiply, you don't have to put over 1. If having the over 1 is helpful to you, then great. When you multiply fractions, just like we did over here, the tops multiply together and the bottoms multiply together. Whatever you do to one side of your equation, multiplying by 5 in our case, you must do to the other side. So 5 times 100 is 500. Technically, that's our answer, but I'm showing you every step that happens here when it comes to canceling. X times 5 is 5x. 5 times 1 is 5. Any number divided by itself is equal to 1. 5 divided by 5 is 1. 1 divided by 1 is 1. 100 divided by 100 is 1. So 5 divided by 5 actually becomes, so 500 equals 1 times x. Any number times 1 is just that number. 1 times 1 billion is 1 billion. 1 times negative 230 is negative 230. So 1 times x is x. All of this that I just did is extra steps to show you how canceling works. You don't ever really need to do that. I will show you how it's normally written. I have n times 2 times pi times 5 divided by 360. I don't like that it's a fraction. Just like how I multiplied by 5 over here to get rid of it on the bottom, I'm going to multiply by 360. If I multiply one side by 360, I must multiply the other side. We get a giant number. I'll go ahead and punch that into a calculator. 360 times 13.4. I can't do that in my head. I don't expect any of you to. 360 times 13.4 is equal to 4824. So I will go ahead and write that here. 4820. Nope. 4. What about 1 times that number? It's that number. Great work. Over here, the 360 is on the bottom. So I multiplied by 360. These cancel out. All I'm left with is n times 2 times pi times 5. Well, what's 2 times 5? 2 times 5, we can combine those together. It's 10. So we have 10 pi times n. I know pi can seem like it's another variable and you're not sure it's just a number. It's just a symbol that we use for a number. So anytime we want to get rid of something that's multiplying to your variable, just like here, I have 5 multiplying to my variable. I need to get rid of it. I divide both sides by 5. I have 10 pi multiplying to my variable. If they're multiplying, I must do the opposite, which is divide. 10 pi, 10 pi. The 10 divided by 10 is 1. Pi divided by pi is 1. 1 times n is n. Here is what we punch into a calculator. You want to make sure that whenever you're punching this stuff into a calculator and you have a big denominator of your fraction, you want to make sure that's in parentheses. 3.1415 something. Yeah, the something is a 9. You want to make sure the bottom is in parentheses or else it's going to mess up. I'll show you that. So 4824 divided by 10. And I'm not going to put the parentheses in. I'll show you. 10 pi. I get this big number. That doesn't make any sense in the context of the problem. If you are running into a problem and you get a giant number and your angle looks like this, something went wrong, likely your parentheses. What this is doing is essentially it's reading this. It's going 4824 divided by 10 is equal to 482.4 and then multiplies by pi. So it gets you this number. We don't want that. We want 10 pi to be multiplied together on the bottom. So that's where the parentheses come in. 4824 divided by, in parentheses, 10 pi. 153.55. That's more reasonable. My drawing is not accurate. No, it's not accurate. 155 point. What did I say? 55. I'll put 0.6 degrees. So for the person that said, what happens if you don't have the angle? As long as you have the radius and the arc length, you can solve for it. The same goes for if you don't have the radius. You would plug in your arc measure, you would plug in your arc length, and you do the same kind of steps to get your radius. I am not going to do that example because I want to get to sector area and then the last two pieces that we need to go over. So I'm going to leave this as is and move on to sector area. I'll scroll down. We're going to do sector area in green. I'm so bad at remembering to hit this button again. Okay. Sector area. Also, I appreciate the questions, even if you're just typing the questions so, like, I have more stuff to talk about. I appreciate it. Sector area. So, first and foremost, a sector is a section of a circle created by two radii. It sounds very similar to our definition for an arc, but the difference is an arc is the part of the circle that connects the endpoints of at least two radii. So it's specifically this part of the circle that connects the endpoints. A sector is that entire section of the circle. So let me draw it again. I have to draw another circle. Okay. I'm going to throw this out the window. I keep not hitting this. Okay. How much pi do I know? 3.14159 and I think 2. And that's it. So here we go. A section of a circle created by two radii. Connected there. Connected there. I am so bad. Okay, there. This section in here. I'm going to, I guess, fill it in with green. This section in here is a sector. I like to call it a pizza slice or a pie slice. It is a little triangular piece of your circle. So a sector is the sector area formula is very, very similar to the arc length. I will write the arc length first to do it again and show you. So arc length. Where'd it go? Okay. Arc length is S equals N over 360 times 2 pi r. Again, this is the ratio of what degree measurement is it's compared to the full 360. So it's like a percentage times the circumference of the circle, the distance around the circle. Sector area is very similar. Sector area. They didn't give me a letter to use, so I tend to go A for area and subscript S for sector. So area of a sector is equal to the same exact fraction, but instead of times 2 pi r, it's times pi r squared. Up at the top, I said 2 pi r was its own equation, and so is pi r squared. Pi r squared is the area of the full circle. All of my streams are going to be saved, so you can watch these whenever you want. So if you got to go have dinner, go for it. But it'll always be here. And if you have questions about this, you can message me, or if you are one of my students, you can tell me at school. Anyway, so pi r squared is the area, 2 pi r is the circumference. 2 pi r, like I said, is the circumference. Sorry, I'm multitasking. And so what we did here for arc length, 2 pi r, it times the percentage of the circle that is our arc, gives us the percentage of the circumference that is our arc length. Sector area does the same thing. It gets the full area of the circle, but then multiplies it by the percentage of that of how much that circle, this chunk, is taking, and it gives you the full area of just what I call the pizza slice. it has the same two variables that we need to solve for. Arc length has N and R. Sector area has N and R. Okay, so that highlighter doesn't show up. Whatever. They have the same number. It's the same numbers that you're searching for. You're searching for the arc measure and you're searching for the radius. That's all we need to solve for this. So let's go ahead and do a quick example. Let's say our arc measure is 60 degrees. And let's say our radius is 8. We need to find how much of the circle that this sector takes up. So let's plug in our values. Area of a sector is the arc measure divided by 360. Well, what's our arc measure? 60 degrees. Times pi times r squared. Well, r is our radius. Our radius this time is 8 squared. I'm going to reduce this fraction. I chose 60 because it's an easy number to work with when it comes to 360. 60 goes into 360 6 times, so this becomes 1/6 pi 8 squared. 8 squared is 8 times 8. 8 times 8 is 64. I'm going to combine them all into one fraction again. Area of a sector is equal to 64 pi over 6. I see that these are even numbers. I'm going to reduce them. You don't have to. You're going to get the same result if you plug it in up here as you do down here. I am just showing you how to reduce it and why I like doing it. Again, you can plug this in as is into most calculators, and I'll even do it at the end and show you both. But I'll just do this again. 64 and 6 are even numbers, so I know they can be divided. I'm going to divide them both by 2. 64 divided by 2 is 32. 6 divided by 2 is 3. 3 cannot go into 32 perfectly, so I'm leaving it at that. So I have two things that I'm going to type in. I'm going to type in this whole mess, and then I'm going to type in my reduced one, and we're going to get the same answer. I do think this is good practice. As you go further in math, this becomes more prevalent and more handy to reduce things. Not reducing can be a headache as you get further. But let me go ahead and open up the calculator. So I'll do the top one first. 60 over 360 times pi 8 squared. This is exactly how I wrote it in green. That's the second step. So right as you plug your stuff in, you technically can be done and plug it into your calculator, but you may plug it in incorrectly. Make sure your parentheses are always around your fraction to make sure that doesn't happen. Boom. 33.51. I am going to type it in again, but this time I am going to use the reduced version, 32 pi over 3. I'm going to put 32 pi in parentheses. You don't have to because it's on the numerator, but I'm going to anyway. 32 pi over 3. The same exact answer. 33.51. Area of a sector is 33.51 units squared. Whenever you have an area, you're working in square units. I didn't put any units, so if I said inches, this would be inches squared. If I said feet, it'd be feet squared, and so on. As far as if you have other missing pieces, it's exactly the same as we just did with arc length. If we didn't have, up here in arc length, I got asked, what happens if I don't have an angle? Well, we can solve for that angle. What happens if I don't have an angle or a radius here? We can solve for it using the same steps. We will do a radius one, where we're solving for a radius. That way we can work with this square. So I guess I have to draw another circle. You guys can attest. I'm better at drawing circles on a whiteboard. I'll do my same tactic. I am so done with this thing. I keep not hitting the pen and just moving the screen around. Okay. Oh, nope. Ah, there we go. Okay, I'll take that. All right. There's the center. I'll make an arc or a sector. If I can, I'm going to draw from the point. Why don't I just draw from the point? How can I not? Okay, don't freak out. Anyway, let's say our sector area is given to us as 64 inches squared. I'm using the units so you can see how it works. 64 inches squared is this. We don't know the radius, and let's say our arc measure is 30 degrees, not to scale. The numbers will work. The drawing, it's the best circle I've done all day, and you're dealing with it. Okay, so let's go ahead and write our equation again. It's always good practice to write the equation over and over until you have it ingrained in your head. And it's always good practice to have it above in case you accidentally write the wrong one. What was happening on a test that was done earlier in the year is people were mistaking the two equations because they're so similar to one another. So I'm making sure I have my area of the sector equation written. Now I need to plug in the stuff where they need to go. R. Oh no. I need to exit Steam again. Okay. Keep forgetting to do that. Go away. Okay, perfect. Area of the sector is given to us. The angle measurement is given to us. The radius is not. That's what we're looking for. So let's plug our things in. Area of the sector is 64. Our angle measure is 30. Our radius stays as a mystery. I once again chose an angle on purpose that is easy to divide into 360. 30 goes into 360 12 times, so this fraction is actually 1 over 12 times pi r squared. I'm going to rewrite this again so you see how these numbers are interacting. We have pi r squared over 12. We have a denominator to get rid of. If we have something on the denominator, we must multiply it to get rid of it. 12 divided by 12 is 1, so those cancel out. And then we get 64 times 12. I can't do that. 12 times 64. 768. Great. 768 is equal to pi r squared. Really quickly, that's the area of the whole thing. Pi r squared is the area of a circle. So now I know the whole area of the circle is 768. But I don't care about the area of the circle. I care about the sector. Or actually, I already have the sector. It's 64. The whole area is 768. I need to find what the radius is. Sorry, I got confused for a second what I was doing. Anyway, remember that pi is a number. So we can divide by it. Pi divided by pi is 1. So we're left with r squared. Divide this side by pi. And we get, let's see, 768 divided by pi, 244.46. I'll write that. 244.46. Is that what I said? Oh, okay. Perfect. We're not done, though. We have an r squared. I care about r, not r squared. R squared just means r times r. I need to do the opposite of that. I need to do the square root. Just like how we have to do the opposite of what's happening here. We have pi times r, multiplying. So we must do the opposite of dividing to cancel it out. We have an exponent. The opposite of an exponent is the square root. Let me rewrite that so it doesn't look like crap. Square root. Square root. We have to do it to both sides. R squared, square rooted, becomes just r. So whatever this is, the square root of 244.46 will give us our answer. Let's go back here. I'm going to say the square root of, and if you didn't know, this button down here, let me scroll. This button down here, the little negative symbol on your calculator, it says ANS. That means answer. So instead of having to type all this in, I can hit second of that button, and it says square root the answer. 15.6. I'm going to round up to 4. 15.64 inches. Right? I said inches? Yeah. That is kind of all that's really needed for... What is happening? Stop that. For arc, measure, and sector area. They're very similar. The equations can be confusing. So I'm going to pause for a second to see if anyone has questions on these before we move to the last two things. The last two things are very simple, very straightforward, so I want to make sure we cover these bases. Okay, I'm not saying anything, so I am going to move up. Here's all the stuff we've done. Look at all that. This almost looks professional. All right. We are going to talk about what is called an inscribed angle. So when you have a circle, okay. Deal with it. Okay. If you have a circle, we have already established that if you connect two radii to the center, it creates a sector, it creates an arc, and it creates a central angle. It's the angle at the center. It's in the name. But if I was to draw lines that go through... Oh, no. This is going to be a mistake. If I was to do this. So now I have a line that goes from this point all the way down. And it connects this way. Should I do it in a different color to make it easier to see? Hang on. I'm going to restart this whole thing. Okay. Oh, okay. Okay, that's good. All right. So then we got ourselves... I'll put the central angle in red. That's the center. I don't want to hear it. What? No! Oh, wait, hang on. No, we're good. That's the center. We're going to connect. Connect. In red is the central angle. What? Now, in blue... I will draw what's called an inscribed angle. And then I'll write the definition of what an inscribed angle is. So imagine this red line goes, it hits the center, and then continues. Imagine this starting point here. Instead of going to the center, it connects to this guy. So I'm going to try to draw... It's not bad. That's not terrible. You can see that. We're good. All right. This angle here is an inscribed angle. Now, an inscribed angle is... Oh, hang on. My hand's cramping. I'm old. Okay. An inscribed angle is an angle created by two chords. A chord is just a line that's inside of a circle that has its endpoints on the edges. So not a radius, but a diameter is a chord. By two chords, whose vertex is on the edge of the circle. So vertex is just the point where the two lines meet. And so right here, for a central angle, the vertex is the center. For an inscribed angle, the vertex is on the edge. So there's not an equation for inscribed angles. There's not really like a trick or anything. Premier Pokeball. Is that what a Premier Pokeball looks like? Hang on. Nope. Premier Pokeball. I mean, kinda. You got me distracted. Don't do that. I am reading chat, Edwin. Okay. Anyway, there's no real connection. There's no real equation. It's just how they are related to one another. So a central angle is equal to the arc measure. An inscribed angle does not equal the arc measure. An inscribed angle, I Here, this is how I'll write it. A for angle, subscript I. Inscribed angle. An inscribed angle is equal to the central angle, A for angle, C for central, divided by 2. It is half of whatever the central angle is. Edwin, you spelled nerd wrong. I don't want to hear it. No, he's fine. He just has brain rot. You're not banning him. So essentially, if you're given a central angle or an arc measure, you cut it in half and you have your inscribed. If you have an inscribed angle, you multiply it by 2 and you get your central. We'll do a quick example. Let's say this arc measure here is 70 degrees, okay? And I said find the inscribed angle. Well, if the arc measure is 70 degrees, that means my central angle is 70 degrees. That means if I plug it into this little quick equation here, my inscribed angle is equal to the central angle over 2. My central angle is 70 divided by 2. So my inscribed angle is whatever that is. 70 divided by 2 is 35. There's not really any other trick to it. The only time this works, though, is very important. I'll put that in a different color so you can see it. Very important. This only works if their beginning points are the same. What that means is the points where the central angle starts and the points where the inscribed angle start need to be the same points. If they're not, then this relationship doesn't work. If they are, then you can use this forever. And it doesn't matter where those angles end up being. If it's like this, no. If it's like that, or like that, or like that, all of these angles will follow that that rule. So all of these angles will be the same. I'm going to erase those just so we can have this nice little pretty picture. I'm not going to do anything else, different other types of angles and stuff, because inscribed angles are the only ones that are on my students' final. So I don't really need them to be confused. Edwin, I don't need this many emojis in my chat. You're not even in geometry. I will ban you in real life. This was a mistake. We're going to move on to the last thing. We're going to do a chord, what's called chord ratios. And there's one specific type. There's nothing else that really goes into this. I don't know who half of these people are. Edwin is from my higher level class. I don't know who Angel Boy is, unless that's Angel. Oh, it's probably Angel. Both of you leave. You're not even in geometry. You're annoying my geometry students who are trying to learn. If you're invested, then shut up. Okay. Last thing we're going to do today is chord what did I call it? Ratios. How's your project coming along, Angel Boy? So once again, I'll just put a definition. A chord is a line segment with its endpoints on the edge of the circle. So we have one case. In our class, we had multiple cases, 3. But we're only going to go over one that's going to be on the final. And it's this. First, here's my circle. And I'm going to draw two lines in two different colors. So here's one chord. And here is the other chord. They intersect. When you have chords that intersect like this, don't say, guys, I don't need this in my chat. It's all of you, knock it off. When you have two chords intersecting like this, the little lines that are created become small little chunks. I'm labeling them as A, B, C, D. You can label them whatever you want, but just know that A and B are on the one line and C and D are the other. The way that these can be played with each other and interact with one another, A times B is equal to C times D, no matter what. So, why is this important? Well, there's going to be problems where you're going to solve for one of these chunks. And you're going to get information about the others. So let's do that. Let's say A is 4, B is unknown, C is 7, and D is 5. So if I was plugging this into this equation, I need to solve for this missing piece, this missing chunk. All I have to do is plug these values in. What's my A? 4. What's my B? I don't know. It's X. What's my C? 7. And what's my D? 5. 4 times X is 4X. 7 times 5 is 35. To get rid of a number that's multiplying, you do the opposite. So you divide. These cancel. X is equal to whatever 35 over 4 is. 35 divided by 4 is 8.75. That is as difficult as these really get. There's gonna, on my students' tests, there's only going to be a couple problems like this. Everything that has gone over today in this about an hour-long stream is essentially all that's needed for the circles section of the test. We went over radius, arcs, arc measure, arc length. Quick summary on how to cancel things out. We did sector area, a couple examples of that. We jumped over to a new topic, which was inscribed angles, how they interact with central angles, and the simplest chord ratio. Are there anything you guys want me to do an extra problem? I'm pausing for a second for chat to catch up so you guys can tell me what you need from me. If not, I was probably going to end it pretty soon. So give you a second. No. Okay. This video, like my other one, no, Edwin. This video, like my other one, will be saved on my channel. So if you wanted to go over this again, I have it all there. If you want to put me on 2.5 speed to go too fast or slower, you go ahead. That is basically it. Thank you for those who joined. No thank you to all of you who were spamming and annoying each other. It's not what I need from this. Hopefully those who were paying attention and needed this help got what they needed. I'm going to call it there. Thank you again for joining. I'm going to end it. And I'll see some of you who are in my class tomorrow.